Okay, the next thing we're going to look at is sometimes we can cause the equilibrium position to move. Okay, we can cause the equilibrium position to shift towards the right side or the left side, and we will use something called LeChat1a's principle. All right. In LeChat1a's principle, I'll give you the first idea first, okay? So, let's say you're at equilibrium, okay? We have to be at equilibrium, okay? We already reached equilibrium for this A goes to B equilibrium equation here. Let's just say we are at equilibrium. And clearly, I'll circle the B's. Clearly, there are more B's than A's, okay? So, at equilibrium, in this situation, the equilibrium position lies to the right. The equilibrium position lies to the right. Because there's more right side particles, or product particles, B. We can do things to this system. This system is at equilibrium, okay? The amount of A and B don't change. Right? The amount of A and B don't change. Now, we can do things to this to cause the equilibrium to shift. Shift means the equilibrium position moves. Maybe we can do something to it. All right, this is called a perturbation. Perturb. The word perturb means just to bother. Okay, to bother. We can bother the system. Like, for example, we can heat the system up by heating it up, and then we can cause it to shift. We can cause, for example, we can cause it to shift to the left side. A, and now I'm trying to draw you a bunch of A's and less B's here. Okay. All right. So I'm circling the B's here. So you can see that I've caused the equilibrium position to shift towards the left. Okay, shift left. Alright, and so we're going to use something called LeChat1a's principle to learn whether it's just to the left or to the right. Okay, that's what we're going to do now. And when we do this, so how does it work is this thing here. So when a system is at equilibrium, okay, so when a chemical reaction is at equilibrium, so chemical reaction at equilibrium, okay, so we allowed it enough time to reach equilibrium, right? And so it's at equilibrium. Now when a chemical reaction is at equilibrium and I do something externally, okay, to the system, I perturb it. A perturbation will cause the equilibrium position to shift in an opposite manner, okay? An opposite manner. Opposite manner. Okay? Alright, so let's see how this is going to work. Okay? So first off, let's assume we have our simplified A goes to B in equilibrium. Okay? And what I will do is, let's just say the system is at equilibrium, okay? So let's just draw some for a visual. We have some A's and B's. I'll circle the B's so we can see them easily. Here, clearly, the equilibrium position lies to the left because there's more A, right? So it lies to the left. Now, I'm not going to do anything to this system. And if I don't do anything to this system, then the amounts of A's and B's remain. here I count 5 A's and 2 B's. Now if I do something to the system, if I perturb the system, it will cause the equilibrium position to shift in an opposite manner. Okay, so for example, what I can do is I can add A to this system. Okay, so I add A. Okay, I'm adding more A to this equilibrium system. What's going to happen is the system says, hey, there's too much A's now. We have to make more B's. Okay, so and in order to make more B's, the system removes A to make B's. Okay, so over time, when I add A to this, it depends on how much A I add, but I'm just going to make something up real quick, just so that we can get an idea of this. Okay, there's still a lot of A's, but guess what? Now there are more B's. Okay. Okay, so before, let's just exaggerate it a little bit more. Okay, what you're seeing is that the equilibrium position has shifted to the right. Shifted to right side. Because before there was only 2 B's. Now when I added A, the opposite would be shift to the right. Now when you shift to the right, what does that mean? That means more A's are turning into B's. Okay, so A is being removed. A is being removed. Hence, the opposite manner, okay? I add A. Well, if I add A, the opposite of adding A is removing A, right? So that must mean every time A disappears, removed, it has to become a B, because you can only have A and B. And recall, if A disappears, then that must mean B appears. So you shift to the right side, okay? Adding A causes the equilibrium to shift to the right side, towards B. That is, to remove A, which is the opposite. A perturbation will cause the equilibrium position to shift in an opposite manner, okay? So the opposite of adding A is to remove A by shifting to the right. That is, A particles must disappear to make more B particles. Now, okay. And I'm just going to keep this panel here. I could also add B particles, okay? Okay, I'm going to add B now. If I add B particles, what will happen is it's going to shift to the left to remove B and to make more A, okay? So shift left, okay? By shifting left, that means the equilibrium position is shifting to the left, B is turning into A. That is, B is being removed, the opposite of adding B, right? All right. In those both cases, I was adding a reactant or adding a product. You could also remove a reactant. So if I take out A, I remove A. If I remove A, the equilibrium system says, wait, we don't have enough A's. We have to shift to make more A. We have to shift to the left to make more A. So shift left. Okay, it's the opposite. It shifts A to make more A. Make more A. Because in this case here, I am removing A, right? Removing A. So it shifts left to make more A, okay? And then of course the opposite is true if I remove B. If I take out B, what will happen is the equilibrium says, hey, I have to make more B, I need to shift to the right. Shift to the right to make more B, which would be the opposite of removing B, right? Okay, so when these are removing amounts, okay? So usually these are concentrations. So concentration is the amount of stuff per unit volume. So notice that these particles are in the same volume. So, so concentration is the amount. Just think of concentration as an amount per unit volume. Okay. They're all in the same volume though, so they're all bouncing around, right? So if you remove concentrations of B, because if you take B out, then you're decreasing the concentration, right? then it's going to shift to the right to make more B. It'll increase B concentration. Now it'll shift towards that way, okay? Now it's really a compensation, okay? And this has to do with the equilibrium constant calculation, actually. But that's advanced, we won't do that. Alright. There's more, okay? Let's assume these are gas particles, okay? And we're going to add more gas particles, okay? So we have A gas particle plus B gas particle. Let's put a 2 here, and then this is in equilibrium with 2 C gas particles, okay? First, before I talk about this one though, just know that, let's just say you have a balloon, and these balloons have the same volume. And this balloon has a lot of gas particles, okay, a lot of gas particles. This one has only a small amount of gas particles. And if I was to ask you, which one do you think has more pressure, okay, pressure? In other words, when you squeeze these balloons, which one is going to be softer, low pressure? Or which one of these, when you push the balloon, it barely moves because it's so tight? This is going to be higher pressure, okay? Higher peak pressure. This one's going to be lower pressure. I think most students would understand that. Because there's more stuff in there bouncing around. These are considered gas particles. These are also gas particles, but there's not that many, okay? People should understand this because, you know, we understand what an inflated tire or a flat tire looks like, and if you pump up a tire too much, it's like bulging, right? So it makes sense that this visual of the balloon is higher pressure and this one is lower pressure. Okay, so I hope I have enough battery. Anyways, so what we do here is we count the total number of moles of reactants in the balanced chemical equation. Okay, number of moles of reactants, R's reactants, number of moles of reactants in balanced equation, balanced chemical equation, okay, which would be 1, 2, 3. Okay, 1, 2, 3. There's 2 A's and one B. 3 moles of reactants, okay? On the right hand side, there's only 2 C's, so there's only 2 moles of product, okay? Usually there's more product, but in this case there's only C's here. Alright, so let's draw a picture. Alright, let's just draw this picture here, and let's just say, you know, there's A's and B's and C's in here. And we're at some equilibrium, okay? We're at some equilibrium. And what I'm going to say is, what would happen if I take this balloon and I increase the pressure by squeezing the balloon to make it smaller? Okay, so I am the perturbation. I'm going to bother this equilibrium chemical reaction by increasing pressure. Okay, I will do it. And when I do that, the system says, hey, I gotta shift. I gotta shift to the right. Why? Shift right. Because if you shift to the right, 2 of A's and a B must collide to become 2 C's. So 3 particles now become 2 particles, right? 2 of the A's and a B here must collide with each other, disappear, and become 2 C particles. 3 particles have become 2 particles. So if I increase the pressure, it's going to want to shift towards to become less particles. Okay, it's going to want to become more like this. It's going to want to take the many particles over here, and it's going to want to become less overall particles. So it's going to shift towards the side with the less amount of particles. Okay, so here's only 2 moles, over here there are 3 moles, right? So it shifts to the right so that it could look more like this. When it shifts to the right, since there are less particles, the pressure decreases, okay? So that's the opposite, all right? And then likewise, if I decrease the pressure, okay, just to say if I decrease the pressure, what will happen? It's going to say, hey, I need to increase the pressure. How is it going to increase the pressure? It's going to say, hey, these 2 particles, let's go make 3 new particles. It's going to want to go to this higher pressure visual here. And so it shifts to the left. And by shifting to the left, it increases P. Okay, so P increases. It wants to do the opposite, okay? All right, now in this case here, on the reactant side, there were more particles than on the product side. We could get a different situation, right, where the product side has more particles. So let me give you that situation. So let's just say A plus B is in equilibrium. These are gases, okay? This only works for gases. G for gas. And then also we make whatever. Let's make 5 C gas particles here. Okay, so only 2 here, right? 2 moles on the left side of reactants. And here there are 5 moles. Let's just make it even more exaggerated. 6D gas. So over here there's 11. 5 plus 6 is 11 moles of product. Okay, 11 moles of product here. So in this case here, on the product side there's more. So again, we have some equilibrium. We don't know how much, we don't care. We just know that we just know that there's some equilibrium here. If we try to increase P by squeezing the balloon smaller, it's going to say, hey, we're going to shift to the left because these 11 particles can become 2 if we shift to the left. And we want to shift to the left because we want to get this picture, a lower pressure environment. So shifts left. Alright, which would lower pressure, which is the opposite, okay? And then also the opposite is true for this situation. When you have more product particles, or moles of particles, or moles of product, if you decrease pressure, if I decrease the pressure somehow, in order to decrease the pressure, I would have to try to expand the balloon. It's going to say, hey, I want to increase the pressure. I want to shift to the right, so two reactant particles can become 11 moles of product. Okay, so by decreasing the pressure, it'll shift right. Okay. All right, my battery's dying. I'm gonna stop this. Actually, let's keep going. Let's see if I can keep going. All right, so that was pressure. Okay, so we have played with using LeChat1a's principle by playing with the amount of stuff, adding A or removing A, and then we did pressure for gases, okay, increasing pressure, decreasing pressure, and now we're going to do another one, temperature. Temperature. For temperature, we always, when we write a reaction, we don't care about how many reactant particles there are, okay? Let's just say we have A in equilibrium with B. Now, written from left hand to right hand, A going to B, okay, reactants are always on the left hand side and products are always on the right hand side. In this process, A going to B, heat sometimes can be made, heat. Okay, heat can be released. Okay, and when heat is released, I can use a thermometer and say, hey, the reaction is causing heat to form because the temperature would rise, okay? T increases, okay? Reading from left hand to right hand, okay? Left hand to right hand. So, left to right is heat is being released. They also might call this an exothermic reaction. Okay? Alright, so as A turns into B, and it's going to release heat. It's an exothermic reaction. And I'm going to have to stop it here. Okay, so Alright, so let me continue this talk. Alright, and what I'll just say here is that, again, it's an exothermic reaction written from left hand to right hand side. And so from left hand to right hand side, if T goes up, that means hot. It's getting hotter, temperature's rising, right? That's what I'm trying to say here. So left to right is hot. This is an exothermic reaction. Now, if that means that the reverse of this is cold, okay? We need to be able to identify this. Usually I'll tell you this, okay? Okay, and so imagine we have some equilibrium reaction, and we are at equilibrium. Okay, we've reached equilibrium. And what I do is I increase the T by heating this up. Okay, I heat this up. What this equilibrium will do is it'll do the opposite. It'll shift to the left, which is cold. It'll do the opposite. I make it hot. I make this hot by adding fire as my fire. It's gonna do this. It's gonna say, oh, I'm gonna shift to the left to make it cold. Shift left. Okay? And of course the opposite is true. The opposite is true if I decrease temperature. I put this in the freezer, for example. It's gonna say, hey, it's cold in here, I'm gonna shift to the right so that it makes it more hot. So it increases T, right? So it shifts to the right. Remember, I would have to give you this information though, okay? So I would have to say like the delta H here is like equal to negative 500 or something. Remember, negative enthalpy means it's exothermic, right? Exothermic means that as A goes to B, written from left hand to right hand side, energy is released. The temperature gets hotter, okay? Now, sometimes we have endothermic reactions. So let's assume we have an endothermic reaction. That means that when you go this way, it's cold, okay? Again, I would have to tell you this information. And then of course, if that means that this way is hot, and then all this changes down here. If you're at some equilibrium position, what I could do is I could increase T by adding fire here. It's gonna say, hey, I'm gonna shift to the right, because the right is cold. Shift right. Okay. Or, the opposite is true. I can make it colder by putting in the freezer. I can decrease temperature, and it'll say, hey, I'm gonna shift to the left, which is hot. Shift left. Okay, and that is it. Those are all those shifting the equilibrium position using LeChat1a's principle. It could be concentration, the amount of stuff removing or adding. It could be pressure of gases in equilibrium, or it can be changing the temperature. Remember that in gases you need to know how many reactant particles are. When changing the pressure to shift the equilibrium, you need to know how many reactant particles there are and how many product particles there are, so you know which way it shifts. In shifting the equilibrium position by looking at the temperature, you need to know whether reading from left hand to right hand side is it exothermic or endothermic. Okay?